Hello, my name is Debomita Basu, and I'm a PhD candidate at Carnegie Mellon University, and I'm very excited to present my talk on the in situ characterization of the Balling phenomenon in additive manufacturing. Before I do, I'd like to give a quick shout out to the Material Science and Engineering Department, the Mechanical Engineering Department, and the Next Manufacturing Consortium at Carnegie Mellon University for helping make this research possible. This is a brief outline of how my talk today will go. I'll give you a little bit of introduction on laser powder bed fusion additive manufacturing and the Balling phenomenon, the methods that were particularly helpful in studying this phenomenon, why we want to study this phenomenon, before showing you some cool in situ videos that I was able to capture. So without further ado, here we go. Additive manufacturing refers to the set of processes that build a three-dimensional part layer by layer. There are several different types of processes, but for the purposes of this work, we're only focusing on laser powder bed fusion. Laser powder bed fusion uses a laser as its heat source and metal powder as a material feedstock. Basically, you spread a layer of powder over the build plate, and the laser melts a two-dimensional pattern for that layer, and you repeat this process over and over again until you end up with a three-dimensional part. Now, there are some defects that are fairly common in laser powder bed fusion, and they're mostly due to processing parameters. The two most important processing parameters that we're looking at are laser power and laser velocity. At a very high laser power and a low velocity, you end up with keyholing, where you have narrow melt pools that are very deep. This depth isn't necessarily a problem. However, this type of melt pool shape is usually accompanied by porosity, and that is the problem. At a low laser power and a high laser velocity, you have a difficult time making sure that your melt tracks overlap properly, causing fusion errors. And this manifests as very jagged shaped pores in your three-dimensional part. So this is also not desirable. You might think that at high laser powers and high laser velocities that you lessen the severity of these types of problems. And to some extent, you'd be right. However, this is where you start to see the Balling phenomenon occur. Now, this is a good time to ask, if we know this defect occurs at high laser powers and velocities, why are we looking there? What is the advantage of these parameters to begin with? And the answer to that is that at these parameters, we get the fastest build rates for this process. Laser powder bed fusion isn't a particularly fast metal additive manufacturing process in comparison to some of the other ones out there. So finding ways to speed up the process is very important. Laser powder bed fusion is also known for its nice small melt pools. This translates as good build resolution in your 3D parts. So if we can find a way to use these high laser powers and velocities, we can potentially find ways to quickly build parts that still have very good build resolution. So now I'm going to talk a little bit more about the Balling phenomenon. As we know, it occurs at high laser powers and velocities, and the melt tracks appear pinched to form discontinuous beads in the worst case scenario. But usually you see super elevated regions along the length of a melt track. There are several things that can influence this, and the leading theories are that the geometric aspect of the melt pool is driving this phenomenon, and there's another theory that's proposing that it's more fluid dynamics based. These are just some micrographs of what the Balling phenomenon looks like from a top-down perspective. You can see these super elevated regions, and you can see how the tracks are pinched. And you can definitely see from these cross-sectional images cases where the material has pulled away from the center line, from the substrate towards the center line, and developed this almost circular cross-section. Now, as I mentioned before, one of the major explanations for this phenomenon is the plateau-Rayleigh instability. And the plateau-Rayleigh instability basically says that for a vertical cylindrical jet of fluid, this jet is stable so long as it meets this criteria, where the ratio of the length of the jet to the width has to be less than pi. This isn't the only stability criterion out there for this particular situation. In fact, additive manufacturing this method of additive manufacturing doesn't really deal with the vertical cylindrical jet of liquid. We have more of a horizontal supported cylinder. And so that changes the stability criterion a little bit to give us some extra stability that's accounted for with that substrate underneath the track. Other laser welding studies have supposed that this critical ratio only needs to be less than 2 pi. So what we can take away from this is that there's clearly not a great consensus here about what this critical number should be. However, there seems to be a general consensus that this ratio of the length of the jet, which translates to melt pool length roughly in our scenario, and melt pool width, that this ratio is important in governing this phenomenon. So there, the instabilities kind of boxed in for you. The less common explanation for this phenomenon is fluid dynamics based, where we know that at the back end of the melt pool there is a ramp, and at these very high laser powers and velocities, the melt accelerates up the ramp as the laser is traveling in the direction indicated by the arrow. The melt is traveling up the back ramp and accumulating into this bead at the surface. This bead continues to grow until the melt pool connection to the bead is severed as the laser moves far enough away. Once this happens, solidification proceeds to take over and bottlenecks the bead up, as you can see on the left-hand side of this figure. Perhaps more importantly of note, in order to actually test and study this phenomenon, we need to have technology available to us that actually lets us observe things at this time scale. Solidification is occurring in sub-second timescales, so we would need to have technology that can also observe the phenomenon at this time scale. And this is kind of where our experimental methods comes in. We conducted single bead experiments on stainless steel samples. Single beads are basically when you use the laser to just melt a single line, typically, into your substrate. You can have powder present or absent, depending on what you're trying to look at. Single beads are very cost effective and fast. We used analytical simulations in addition to our experiments to help with predicting melt pool dimensions, so I'll talk about that on the next slide. And lastly, we used in situ imaging techniques. This is a picture of the setup at Argonne National Lab for the experiments that we conducted. And for your reference, the x-rays would be coming in from this side. Analytical simulations are relatively fast calculations that can be made before or after you run your experiments. As long as you know what parameters you want to input, you can run these at any time. There are several input variables that affect these predictions, namely laser power and velocity, absorptivity, which is a number between 0 and 1 that gets multiplied with the power to give you an estimated absorbed power. The evaluation temperature is also an input variable that affects the thermal properties used in the particular simulation. Now, the reason why analytical simulations are so fast is they're not accounting for temperature-dependent properties. They're only using the properties at one temperature, but the user gets to specify that temperature. Lastly, preheat temperature is another input that can be accounted for in these simulations. This is worth considering as in a normal sense, when you're building samples with these metal powders, you are typically going to be using a preheat temperature that is higher than your standard room temperature. So understanding how preheat temperature affects your melt pool geometry is typically useful, since when you're actually building a part, you won't necessarily be operating at just room temperature. The analytical simulation that we used in this work is the Eager-Psi model, which allows us to input a spot size. And this model is a superposition of the Rosenthal model. Finally, we used in situ imaging techniques to help us study this phenomenon in real time. And the reason why we wanted to use high-speed imaging techniques is so that we get this really nice temporal and spatial resolution. As you can see from the schematic, the X-rays are coming in from the side and allowing us to see this melting process from a side perspective which is particularly interesting. So to kind of summarize everything thus far, we want to study this phenomenon in the context of the proposed explanations that are out there. And the proposed explanations that are out there are the plateau-Rayleigh instability and related criteria, which depend on this melt pool length to width ratio. Well, melt pool length is only measurable by in situ techniques since solidification plays a very big role in melt pool length. However, this quantity is predicted by analytical models. So this raises the question of how these predictions compare to actual measurements of the melt pool length. The second explanation for the balling phenomenon is fluid flow. And because of the sensitive timescales involved in fluid flow, we can only study this with in situ techniques. So with that, let's dive into the results and discussion. Some preliminary experiments using the high-speed X-ray imaging capabilities at Argonne National Lab showed us exactly what we might hope to see from the side perspective of the melting process. So the video that is currently playing is showing you, yes, the laser, the track is coming into view. That is the vapor cavity underneath the laser. And the laser parameters are 350 watts and 800 millimeters per second. So we can see this nice vapor cavity. We can see liquid moving from the front of the melt pool towards the back. And we see a relatively smooth melt pool. Now, if we increase both the laser power and the laser velocity, what might change? And now we see the track coming into view. We see a much shallower vapor cavity, but also a much longer one. And more importantly, we see the formation of the balled up regions. This is pretty exciting, as this is a novel perspective of looking at the formation of balled up regions. We're able to actually see it from the side perspective. We did several more experiments like this, and we're able to compile a vapor cavity process map of sorts, where we can see how the shape of this vapor cavity changes with laser power and velocity. At a fixed velocity, increasing the laser power increases the size of the vapor cavity. But at a fixed power, increasing the velocity makes the vapor cavity shallower but longer, usually. I've used a red dot in some of these figures to indicate which tracks, which laser parameters cause the formation of balled up regions. In addition to this high-speed X-ray imaging, often referred to as dynamic X-ray imaging, or DXR, we were able to use some synchronous infrared imaging that can be done from overhead. The main purpose of using IR imaging is that it allows us to get an estimate of the temperature along the melt pool, which lets us see whether solidification is occurring. And this is particularly important given the fluid flow explanation for this phenomenon. It's worth mentioning that in order to get this estimate of temperature, we have to go through a calibration process that requires the use of the high-speed X-ray imaging, or DXR video. But the main reason why infrared imaging was used is so that it can help us see whether solidification is occurring between the balled up regions that may be causing the phenomenon. So we're able to do these combined infrared and high-speed X-ray imaging videos. Now, this is a parameter that doesn't result in the formation of any balled up regions. And you can see that there was a very nice vapor cavity that formed and a very smooth melt track, as we can see from above. I also have these red and white lines overlaid on the top video, indicating what the eager-side predicted melt pool dimensions for width and length would be based on these particular absorptivity values. So those are there just as a reference to compare to the actual length of the melt pool and length and width of the melt pool. So this was a powderless case where we did not see balling. So what might we see in a powderless case where the parameters are more likely to yield balling? Well, we see balled up regions along the surface, and I'll play that again if I can. And we also see that solidification is occurring in between these balled up regions while the tops are still remaining liquid. So this is pretty exciting. Now, these experiments so far have been powderless. If I take this exact parameter and add powder, what might that look like? As you can see, you can kind of see the formation of balled up regions. However, the powder flying around everywhere makes it a little hard to see things. But it's good to note that we can see balling in both the powder less and the powder added cases. Now, some of those videos may have been fast, so I wanted to just take some still shots from the powderless experiments. This is from the first set of experiments, which did not yield balling. And this is from the set of experiments that did yield balling. We can see that for this set of parameters, pretty much the entire length of the track is liquid. However, the next track, you do see that the temperatures in between these balled up regions are slowly cooling down while the surfaces of these balled up regions are still very much liquid, suggesting that solidification is occurring in between those balled up regions. We were able to use the IR imaging to acquire melt pool length and width measurements. And we compared these to the model predictions of these melt pool dimensions at different absorptivities, at 2 fixed values of absorptivities. And as you can see, we don't really get very good agreement, especially on length. Good agreement would look more like the data points lining up on this dashed line. But we don't really see that for most of these cases. So if we want to talk more about possible reasons why we get this poor agreement between the predicted dimensions and the actual dimensions, we should take a look at the simulations and the experimental setup. And we know that the analytical models make several simplifying assumptions. And we know that the laser additivity drastically affects the length predictions, as we saw from those overlays, the red and white line overlays on our infrared images. So it's very possible that the model may not be accounting for something. On the experimental side, the pixel resolution in the infrared images is 30 microns, which means that the measurements could be plus or minus 30 microns, which is not a particularly small amount to be uncertain about. The melt track length of 2 millimeters that was used for these in situ experiments might be too short for experiments. Though there is some work in the literature suggesting that a length between 1 millimeter and 2 millimeters is sufficient enough for the track to reach steady state, some of these measured melt pool lengths are very close to 2 millimeters. They don't exceed 2 millimeters, but they get pretty close. It's possible that we might need a longer melt track length. And the reason why we had picked 2 millimeters from the start is that 2 millimeters is approximately how wide the high-speed X-ray imaging frame is. So a possible fix for this is to run a longer track, but focus the high-speed X-ray imaging towards the center of this very long track. As I mentioned before, there is a calibration procedure for these infrared images. We use the high-speed X-ray images to estimate how long the melt pool is. Then we return to the infrared images to see what the reported black body temperature is at that particular distance away from the front of the melt pool on that exact frame, on the corresponding frame. And then we're able to calibrate the temperature to the solidification temperature. This process was done several times to make sure that we were getting temperatures that we perceive to be reasonable, but it's possible that further processing may have been necessary in this work. With that, I'm going to wrap up with my conclusions. We know that in situ imaging techniques can be used to study the balling phenomenon, but we also know that the analytical model predictions disagree with the measured length of a melt pool. And this could be due to a variety of reasons, like the ones that I summed up on the last slide. I would like to take this moment to thank my advisors, Dr. Jack Buth, Dr. Brian Webler, the staff at APS, including Benjamin Gould, who was particularly helpful in this work, as well as my colleagues at Carnegie Mellon University. Thank you for coming to my talk. My email address is listed below, as well as my LinkedIn. Please let me know if you have any questions, and have a great day.